All right, so this is lecture 7 of this course, Quantum Mechanics for Mathematically Minded People. So let me first go back to the last lecture and just briefly to remind what we did last time. Sorry. Okay, so last time I introduced some basics of quantum mechanics. And by basics, I don't mean the physics basics, but mathematical basics. The basic mathematical structures and formal structures in quantum mechanics. So first structure is the algebra. So when I'm defining this, I mean the following, that if we have a quantum mechanical system, if somebody say that here is the quantum mechanical system, these are the first things that should be defined. So the algebra of observables. It's a little bit misleading term. It's an algebra of observables over C with star involution. So it's anti-involution. So it's an involution, which is an algebra anti-automorphism. So double star is A double star is A, and lambda A star is lambda bar A star. So it's C antilinear. And then there is a real subspace in this complex vector space AC. So let me maybe call it AC. Real subspace. You can think of this as a subspace of Hermitian matrices inside of n by n complex matrices. So this is the space of all elements such that A star is equal A, so fixed points of star. So these are observables. So you can say that algebra of observables is a complexification of this space, and now on the complexification you have a natural, you may have an associative algebra structure. Okay, so then the other important thing is star representation. Of AC, so which means that it's an algebra homomorphism from A to endomorphisms of some Hermitian space. And it's Hilbert space, meaning it's completed in the L2 topology space when it's infinite dimensional. So these are the observables. So the algebra of observables, the space of observables, and a star representation of the algebra of observables. So these are the kind of basic, very basic structures. Two examples. First, these are n by n complex matrices. Then the space of observables are Hermitian matrices. and the our Hermitian space is just Cn with the Hermitian form and the standard Hermitian form. So this is a finite dimensional model of quantum mechanics. And, you know, if you study spin systems or quantum computing, quantum information, very frequently these are finite dimensional spaces, finite dimensional matrix algebras, and this is the sort of basic thing that you need. So that example is when the algebra of observables are differential operators, say on Rn. So differential operators here with smooth coefficients. So in this case, OC are formal self-adjoint operators. And so, for example, if n equals 1, so these are the differential operators of the form sum over, well, I ddx.
Sorry, what are the complex coefficients in diff Rn?
Sorry?
What are the complex coefficients in diff Rn? Well, what is?
Oh, these are just sums of differential operators. So this is a multi-index. So it's the following.
Okay.
So it's
Ah,
sum n1 k1 kn finite sum ddx1 k1 ddx n kn, and then some complex valued function x1 xn, and they have to be formally self-adjoint, meaning that a star should be equal to a, and the rule of the game is that ddxi f star. Oh, sorry, that's all. Just differential operators like this. C value. So this is the algebra of observables. The star involution is the following. It's just ddxi f star, it's equal to f bar ddxi. I think it's like this. Is it clear why it's minus? So the Hermitian, yes, yes, so I didn't, so maybe I should say that this is a subalgebra in the algebra of endomorphisms of the Hilbert space, which is the space of functions, complex valued functions on Rn, with the Hermitian scalar product like this. And then what does it mean, Hermitian conjugate? So it's dxif psi p. By definition of the Hermitian conjugate, is ddxif star phi c. So let's compute it. Integral phi bar df, oh no, sorry, it's composition of operators, multiplication and dnx. So this is equal to, now I use the Leibniz rule, df dxi c plus phi f d psi dxi. Okay, dnx. So then I use integration by parts in the last piece, and I have minus. I mean, all functions should decay, otherwise this is not a Hilbert space. So we assume that the norm of each function is finite. That means that at least they decrease at infinity. So this is minus integral over Rn, and then dxi phi bar f psi plus integral over Rn phi df dxi psi. Okay. So dnx. And then I use the product rule. And you see, this is minus Rn d phi dxi. I'll write f to the left, minus, when I differentiate f, it will be phi bar df dxi c dnx plus this term. And you see that this and this will kill each other. So the result is Rn, and here we have f bar minus ddxi. This we apply to phi, and then we do overall complex conjugation, c dnx. And so you see that this is exactly what I wrote over there, except, no, even with this, with the minus sign. So it's minus ddxi phi psi. So that means that ddxi f Hermitian conjugate is f bar minus ddxi. So this is how the Hermitian conjugation acts on generators. And then you can kind of continue to higher order monomials in derivatives. So one of the important corollaries that ddxi is formally anti-self-conjugate. If you want to have self-conjugation, self-conjugated differential operators, we have to put I. So this is formally self-conjugate. We just have to check that it's really self-adjoint operator in the sense that the domain where the differential operator is defined is the same as the domain of the well, we have to do some spectral analysis, which I don't want to do now. So this is actually, in this case, it's formally self-conjugate and it's self-conjugate. What I did is actually proof of the self-conjugacy. Okay. So this is the star involution. And then our observables are just formal self-adjoint operators. For example, I ddxj self-adjoint minus this differential operator plus any multiplication by a real valued function is self-adjoint. And
By the way, should this be OR or is it OC?
OR, yes, of course. Okay, and I already constructed Hermitian representation, so this is a second example. Okay, and this will be two basic examples. We will consider finite dimensional matrix quantum mechanics, and maybe another example will be, which is sort of standard example, is the algebra of differential operators on some smooth manifold Q. So differential operators and Qn is a smooth manifold. And of course, 2 is a deformation quantization, which we discussed last time, of functions on T star Rn, which are polynomial in the cotangent directions. And third example is deformation quantization of functions on T star Qn. Again, polynomial in T star directions. If you will remove the word polynomial, then this will be so-called pseudo-differential operators. Okay. So we will discuss deformation quantization aspects later. So now let's discuss. So we have. So these are the examples. So we have basic structures as the algebra of observables, the space of observables, star representation, and now states. So states, without going into functional analysis, I'll just say it like this. These are positive linear functionals on the algebra of observables, positive means the following, that first, okay, on the subspace of observables, rho of A is real.
Sorry,
Uh-huh.
just to backtrack to point number, well, three gives definition quantization of C cotangent bundle of Qn. What does it mean to take polynomials in the T star or in the cotangent direction for cotangent Qn?
Well, it just means that, say, locally, locally, say, let's consider a neighborhood, coordinate neighborhood. So then we come back to the second example in the coordinate neighborhood. So we consider functions that are smooth in Q variables, that's in Q, and polynomial in the cotangent coordinates, P coordinates. Then if we do the coordinate transformation, if we go to the different coordinate chart in Q, we're changing P variables only by the Jacobian that depends on Q.
Mm.
So if they were polynomial in one coordinate chart, they will remain polynomials in the other coordinate charts.
Okay, yeah.
So this notion makes sense.
Okay.
Okay, now states. So these are linear functionals which are real on self-adjoint elements and are non-negative on the self-adjoint elements of this type. So you see, sorry, on elements of this type, A doesn't have to be, so here A is really from here, and here A is from the algebra. And it's equality if and only if A is 0. So you see, if A is the space of n by n matrices, then A star A are matrices with non-negative eigenvalues. So it makes sense to say that these are non-negative elements. And then if our algebra is more complicated, then sort of by analogy, you can argue it's in this way, and then sort of most of the examples can be thought as some kind of approximation by large matrices. Okay, so I think this is all. And if A is represented in endomorphisms of some Hermitian space, then there is a I think it's Stone von Neumann theorem saying that any functional of this type is actually given by some density matrix, but it's a little bit, so I will skip the precise formulation of the theorem. I just will define what is the, so in this case, if rho belongs to endomorphisms of H, such that trace rho is 1 and rho is non-negative. Sorry, rho is Hermitian and non-negative. So non-negative means that this positive eigenvalue, no, sort of real eigenvalues that Hermitian matrices have, they are all non-negative. So it means non-negative eigenvalues.
Wait, sorry. Just to check if I've understood. So for the finite dimensional example before, a general row is something like square root of trace. Is that correct? Well, I mean, maybe not necessarily trace. I guess any sort of.
What do you mean?
Sorry.
So can you say it again? What did you say?
Is row? I mean, is an example of row square root of trace?
Where it should be the square root?
You wanted positive. You wanted linear.
Yeah, these are linear functions.
Yeah. So if it takes in a and it gives out. Oh, I see. It's taking in a hat. I mean, a star.
Yeah, maybe I should say that.
Okay, I misread it. Okay, so it's just trace.
Yeah, row with the state row with the density matrix A is the following. It's the trace representation of A with row.
Okay, yeah. Sorry, yeah.
Which I will denote slow, kind of just like A acting on the space. It's just notations. Bad notations. Bad but convenient. So this state, so this is the state with the density matrix rho. And then the Stone-von-Neumann theorem says that under appropriate assumptions, every state is a state with the density matrix. So it's a typical situation. So again, it's a definition. It's a state with the density matrix rho. And then another definition, if rho is rank 1 projection to the vector psi, phi psi phi is equal to psi phi psi. So this is our Hermitian scalar product. On our Hilbert space. So this then rho t psi is simply the matrix element of A between psi and psi, and t psi is called the pure state corresponding to psi. So then mixed state. No, let's just discuss pure state. So this is a pure state, and now if A is an observable, let's assume that for simplicity that our algebra is just the algebra of endomorphisms of H. It's true for quantum mechanics where observables are differential operators. So, or rather, maybe not the whole space of endomorphisms, but some subspace in the infinite dimensional case. So then A star equals A means Hermitian, so it has a spectral decomposition. Phi, sorry, orthogonal projection to an eigenstate psi A. So A phi I is equal to I. So the spectrum can have multiplicities. Then we just choose a basis in the eigensubspace. So then rho psi A, which is this matrix element. What is this? This is sum over I, AI, and then it's a simple exercise in linear algebra that this is this psi phi I squared. Now, what is this? What are these numbers? Obviously, these numbers are non-negative. And also, it's obvious that sum over I psi phi I squared is equal to 1. Indeed, sum over I psi. Oh, wait, I'm sorry. I'm missing a very important thing. You see, this is a projection, and it's an orthonormal projection only if psi is equal to 1. This is important. It's a normalized vector in the Hilbert space. So all these vectors are normalized. I failed to say that the norm of this of each of these vectors is 1.
So to clarify, we only have the notion of saying pure states for normalized vectors.
So yeah,
Okay.
yeah, it's a pure, yes. Pure states should be normalized. Okay, so what is this? This is so this is just the following. Phi I psi, orthogonal projection to phi I, and this is the same as psi sum over I p phi I psi, but we agreed that this phi sub I, this is a complete set of eigenvectors of the Hermitian operator A. So this is the partition of the identity operator in the Hilbert space. So this is psi, and this is equal to 1. So indeed, sum of these squares is 1. So which means that these numbers are probabilities assigned to I. And in fact, the physical meaning of these numbers is the following. It's the probability that the observable A has value AI in the state, in the pure state psi. That's the meaning of these numbers. In physics, the scalar products psi, so kind of physics terminology, psi phi, they're called overlaps. Why they're called overlaps? Well, roughly speaking, if this is really quantum mechanical particle in Rn, then this scalar product is supported only on the overlap of support of psi and phi. So if function psi is supported in one place and function phi is supported in the other place, then this scalar product is zero. So they have zero overlap. But if they supported, the support intersect, then this is an overlap. And psi phi squared is sometimes they called transition probability. Transition probability meaning transition probability from pure state psi to pure state phi. And that is if you switch on the time dynamics, but this is just the terminology. So what's important is this, that this the physical meaning of this of these numbers. And so you can see that the value of observable on the pure state psi I is the expectation value of eigenvalues distributed with these probabilities. So if you are a non-believer in quantum mechanics, you may start to think, okay, so this is really what this is all about. It's so we have some kind of hidden probability distributions, and that's all it is in quantum mechanics. That we can model these probabilistic aspects of quantum mechanics by some kind of classical statistical mechanics. So that's the idea of hidden parameters. This is what Einstein believed in, and unfortunately he was wrong. So there is a there is a way how to check that it's impossible to have this probabilistic statistical mechanics type interpretation of quantum mechanics. There are so-called Bell inequalities, but maybe I'll talk about them but later. But so far, that's the probabilistic meaning of pure states. Okay, so now, what if our state is not pure? Mixed states. So suppose we have some density matrix, rho, which is, first, let's start with the finite sum. It's just a finite sum. I will not introduce the range of it. Some numbers, and then here the projection to the corresponding eigenvalue. And I assume that these numbers are non-zero. I don't want to count zeros. Rho hat can be very degenerate matrix, like for the pure state, it has all eigenvalues zero except for one. That's corresponding to the pure state. So what do we know about this rho I? They are positive, and their sum is equal to 1. So we have a convex linear combination of pure states. And so when you have convex linear combinations of something, you have the extremal points of these convex combinations, and these pure states that occur here, these are the extremal points of this type of mixing. So now let's look at the, so there are several ways to denote expectation value. This is a mathematical way. This is how physicists denote it. So this is the expectation value of A in a state rho. And according to our definition of the state, this is just trace rho A. And so now let's see what this is. This sum over I, rho I, and then phi I A. Maybe, I want to use Greek letters here, not because I'm religious about Greek letters, just because I started to use Latin letters before. So now this will be alphas. So now I want to use this formula. Where is it? Yes, I want to use this formula for the value of A in a pure state. So this will be sum over alpha, rho alpha, sum over I, AI, and here it will be phi alpha. Maybe I should retain psi for this. I'm sorry. Psi. And phi, as they were, are eigenvectors of A. And so you see, this is just the expectation value with this probability distribution with probabilities psi alpha phi I, and then they are also distributed so we averaging with respect to this probability and with respect to this probability. So maybe, yeah, I will just multiply it. So now this is really, so you can see that these numbers are non-negative and sum over alpha, rho alpha, psi alpha, phi I squared, they sum up to 1. So it doesn't matter whether the state is pure or mixed, you still have this probability interpretation, probabilistic interpretation, so that the value of an observable on this state is given by the probability distribution. I mean, it's an expectation value of this probability distribution on eigen values. Okay, so finally,
this sum equal to 1. Is it sum over alpha or sum over I?
both.
Oh, okay.
Mm-hmm.
All right. Okay. Thank you.
Thank you. So now corollary. if unfortunately it's the same letter, let's say, so if an observable has if this vector is an eigenvector of an observable and it's normalized, then the expectation value on this pure state of A is just equal to A0. So this means that on this pure state, A has value A0. A doesn't have a value on the mixed state. On a mixed state, A doesn't have a value on a pure state, which is not an eigenvector. But if pure state happened to be an eigenvector, then we say that this is a state corresponding to, so this is a state where we observe A with probability 1, and the value which we will find is exactly A0. So A has value A0 on P psi with probability 1.
Sorry, your psi here is a pure I mean, the P psi is a pure state.
Yeah, it's a pure state. Projector, orthogonal projector to psi. Okay, so these are the, oh, just a second. Delivery service. Okay. Good. So then, what else did we discuss last time? We discussed the evolution of states and observables. So let's for observables, it's just the following. Before we define the evolution, to have an evolution, we have to choose Hamiltonian. We need the Hamiltonian. That's an operator in our Hilbert space or element of our algebra of observable, which is actually an observable. In other words, it should be self-adjoint. So its spectrum, you know, so far I was assuming that every self-adjoint operator has only discrete spectrum, but it may have discrete or continuous spectrum. So its spectrum is the set of values of the energy of the system. By definition. So this is, so in order to define quantum mechanical system, we have to define the algebra of observables, its representation in a Hilbert space H. So we have the notion of states, but in order to have the dynamics, really the dynamical quantum mechanical system, we need to fix the Hamiltonian. And in every physical system, there is a Hamiltonian. I mean, if there is no Hamiltonian, it's the theory of nothing. So if the Hamiltonian is zero, like in topological quantum field theory, so physicists say it's the theory of nothing, because there is no energy. So it's the joke of Michael Green that I was observing on the colloquium. His joke was, so there is a beautiful thing like string theory, but then he said there is some people study string theory with zero Hamiltonian, and physicists, he said, would call it the theory of nothing. And then the last slide was called topological string theory is equal to the theory of nothing. That's not me. And that was back in the 90s. So for observables, the evolution is given by this linear differential equation. So let's say that with the initial condition A for density matrices, it's almost the same, but the sign is different. And let's see why the sign is different. In fact, this, I'm kind of doing it in the opposite order. So, so before I'll do this, so what it means is that we can solve these differential equations if we can exponentiate the Hamiltonian. So we can write this is equal to UT inverse A UT, rho hat is equal to UT inverse. UT is called a time propagator, and I think it's minus, so if I'll differentiate it, I'll have minus I. Yeah, I think it's correct. No, it's not correct. It's plus. No, it's minus. So now it's correct. Okay, this is the time propagator. For our quantum mechanical system, and corollary of this definitions is that if I'll take the value of the observable A on the state that evolved from rho to rho t, this is the same as I take the value of the result of the evolution of the observable at the initial state rho. And the proof is trivial, it's just because now I'll use this formula for the evolution, use the secret property of the trace, and I have the evolution of A. Okay. So do we still have time? Yeah. Any questions so far? I think, so what I did is just basically I repeated the last lecture in greater details. And I skipped the deformation quantization part.
So if we take the pi of AT, then it becomes endomorphisms on H.
Yes, yes.
So why is it that we want AT to behave with different signs to rho T?
It's because we want this.
Okay, so even though they're in the same space, we want to think of them as different objects.
Yeah, because they are different objects. One is observable, the other is the kind of quantum probabilistic distribution of the observables.
Okay.
They have completely different physical meaning. They are both given by Hermitian operators.
Okay. So they're sort of like sitting in two different compartments. I mean, one is sitting on the left and one sitting on the right for the bracket, or?
No, they are both Hermitian operators acting on the same space, but they serve different purposes.
Okay.
And in fact, the density matrix is non-negative normalized trace class operator, and observables don't have to be trace class operators. So,
can I think of them like objects that dual to each other, like vector space and dual vector space, and the trace is just a canonical pairing, for example?
I would rather say the following, that the trace is a scalar product on the space of operators. Say, to remove the convergence issues, we can say the following, that suppose that we have complex n by n matrices acting on a complex vector space. So on a complex vector space, we have the Hermitian bilinear form. So that means that on n by n matrices, we have the notion of Hermitian conjugate because of this. So then we can define the scalar product on the space of n by n matrices as so. On n by n matrices, we can define the Hermitian scalar product as trace of A star B. So this makes n by n matrices a Hermitian vector space. And in this Hermitian vector space, you can have vectors of different nature. So you can have self-adjoint Hermitian matrices that are normalized from the point of view of trace. So I think I'm not saying anything intelligent.
I feel like that's what he was actually asking about.
Is it?
Well, I think that I actually can think of rho and A like the dual objects, but we define an isomorphism via this scalar product. So we have isomorphism.
What do you mean dual objects?
Like if you think of finite dimensional space like V and home VC.
So let's look here. So observables here, these are Hermitian matrices. That's a subspace in our algebra, which is this matrix.
Yes, and our rho is just a linear functional on a
States
set of...
are again Hermitian matrices, but with the extra property. They are non-negative and normalized. right? So we have the Hermitian structure. AC tensor AC to C. And then, if I understood correctly, you're saying that these two subspaces, so it's also a subspace in here. Sorry, C. Are you saying that these two subspaces are dual to each other?
In some sort of, I guess.
I think maybe he means like state sits in maybe the left AC and OR sits in the right AC.
Yes, some sort of, because
Okay.
Yeah.
Unfortunately, I have this formula.
Okay, so
So,
all right.
so where is left, where is right?
I mean, most of the time you're writing the rows on the left, right? How often do you want to write them on the right?
yeah.
No, I mean, Daniel, conceptually, yes. I mean, not conceptually, kind of philosophically, one can say that in some sense, if this is the Hermitian scalar product, then you can think of them as being dual, especially in the sense that you want to think about rho as a linear functional on matrices. But once you identified a vector space with its dual, say by this trace formula, then there is
Yeah,
no
I guess.
difference.
Yeah, I guess that's what I meant.
Yeah. So, so philosophically, yes, they live in different spaces, but as soon as we start to talk about traces and not states, but the density matrices of states, we made an identification of them as vector spaces. But the physical meaning is different. But yes, actually, you're right in the sense that this explains the difference in the sign. Because the density matrices, they define the linear functionals on the state. They transform sort of in a dual way, like this, in opposite to the observables. Okay. So,
Sorry, can you go back up slightly? Okay, yeah, that's fine. Okay, good. Thanks.
anything else? Okay, so then let's discuss the uncertainty principle.
Did you say you need to leave 8:30? It's almost 8:30.
Sorry? Yes, so 5 minutes is okay. I mean, I'll do it very briefly and then, thank you. And then we'll continue next time. Or maybe I'll just leave it as a homework. So, okay, so if we have an observable A, state density matrix rho, this is the expectation value of A in the state with density matrix rho. Okay, so where we have, so we also have the dispersion. So let's define the dispersion very naturally, just in the same way as we define it in probability theory. So we just take A minus its expectation value on the state rho, take the square of this, and take the expectation value. That's the dispersion or variance of A in the state. You know, I will not say it every time it's a state with density matrix rho. I'll just say in a state rho hat. And then we have a beautiful theorem that was originally to Heisenberg in the example of really quantum mechanics in the sense of differential operators. And then Hermann Weyl gave this argument that shows that it's a completely general statement. So suppose we have two observables. A and B. Then such that, you know, all these expectation values are fine, so that everything is defined. So then delta rho hat A squared times delta rho hat B squared is greater or equal than 1/4. And then you see, if A and B are Hermitian, commutator A and B is anti-Hermitian. But if you multiply it by I, it's Hermitian again. And so I take this Hermitian operator. So you see that if the dispersion of one state is 0, then the dispersion of one observable, and if the observable is not 0, then the dispersion of the other should be infinity. So we will discuss the physical meaning next time. So proof. So let's leave it as a homework, and hint is the following. Consider this function. A plus I alpha B first, assume that this is a pure state. So if you consider this, it's clearly non-negative, and it's a polynomial quadratic in alpha, which means that the discriminant should be negative for the polynomial to be positive. And then if you will do the homework, you will see that this is exactly the statement about this. And then mixed states, it's a homework. You know, don't listen now, please close your eyes, close your ears. If you will take the book by Takhtajan or by Fadeev and Yakubovsky, or probably many other textbooks, sort of more mathematically minded, you will see the proof of this theory. Okay, so next time we will start with the uncertainty principle, and then we'll maybe discuss a little bit more probabilistic meaning of states in quantum mechanics. And then I think it's impossible to discuss quantum mechanics without a good example. So a good example will be Schrödinger equation, Schrödinger operator, which is the Laplacian plus a potential. And then we will, okay, so then we will see that that's exactly the quantization of the Newtonian particle. And the goal of these lectures at the end is to give to have a careful discussion of the semi-classical limit in quantum mechanics, and just to see the interface between classical and quantum. Okay. Last questions?
Are there any really weird versions of quantum mechanics where you don't have the Hilbert Hilbert algebra, but I mean, you still have countably many generators, but you don't quite have projections, orthogonal projections, as in that they somehow have to have like positive covariance.
Well, there are cases when, for example, the Hamiltonian doesn't have a discrete spectrum. It can only have continuous spectrum. So strictly speaking, it doesn't have eigenvalues and eigenvectors. So in this case, yeah, in this case, everything should be modified. But there is a standard way to do it. So it's, yeah, I think. Otherwise, you know, pure state is a pure state. It's always a vector in the Hilbert space with norm 1. Like a plane wave, for example, if you have something like, so if your space is L2R and you consider the function K some real number, character of the translation algebra, translation group, this doesn't belong here.
I think I really should let you go because it's way past.
Yeah, yeah. Okay. So I'll see you next time, next Tuesday.
See you.
Okay. Thank you.
Bye.
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 Come to Beijing.
What?